On to this Spitalfields day, and before Tobias starts his lecture, I just have to say a couple of words about the history of the Spitalfields days. That I guess people are aware that certainly in the 18th and early 19th century, most science was done outside Oxford. And in fact, there were several mathematical societies, but there was a Spitalfields Mathematical Society which existed from 1717 to 1845, when it had the fate of being amalgamated with the Royal Astronomical Society. Now, there was one person who was a member of both the London Mathematical Society and the Spitalfields Mathematical Society. It's someone called Benjamin Gompertz, who was the last president of the Spitalfields Society and the only person to be a member of both. And curiously, I wonder whether this Gompertz is the same Gompertz, the same family, because it's a very unusual English name, which has a big Korean connection and which gave the wonderful collection of particularly Korean porcelain to the Fitzwilliam Museum. So the high point of the public lectures given by the Spitalfields Society came around 1806, when the number of members of the society was 9 squared. An earlier version of the rules had said that the number of members must not exceed 8 squared. However, lots of people used to attend the lectures, that's different from the members of the society, and more than 300 people attended some of the lectures. And the average attendance was about 130, which is more than we have today. So I'm proud to say I was a member of the Council of the London Mathematical Society in 1987 when this system was set up. It was part of a number of initiatives that Christopher Zeeman pushed to use the wealth of the London Mathematical Society more at the coalface. And, well, that's all I have to say then. We're going to hand over to Tobias to give his first lecture on modularity of Galois representations. Thank you.
Thank you very much. Is this should be working? Yes. Thank you very much. It's a pleasure to give this lecture here today. This first talk, I will basically introduce the actors in our play, if you will, today, and set this scene. And there will be 3 parts to this. Firstly, Galois representations, then modular forms, and then the modularity. So let me start by reviewing what Galois representations are and introducing some notation. So for any field K, I will write G sub K for the absolute Galois group, so for some separable algebraic closure K bar over K, the Galois group, and will mostly be interested in number fields, so finite extensions of Q that I'll view as subfields of some fixed algebraic closure of Q. And the object we're interested in studying is the absolute Galois group of this number field, which can be identified with the inverse limit of Galois groups of extensions f prime over our field f that are finite and Galois. And this identification tells us that we're working with a profinite compact group equipped with the profinite topology that is called a Kroll topology. Now, we don't just want to study this as an abstract group. We quite often want to impose some additional structure. So the additional structure will be a choice for every prime of this field. So for every finite place or prime V of f, I'll fix an embedding of the algebraic closure of f into an algebraic closure of the completion of f with respect to this prime. And fixing such an embedding induces a closed embedding of the absolute Galois group of the localization of f at v into g sub f. And this is the decomposition group at v, at the prime b. And g of v can be well understood. In particular, we have exact sequences. So if I denote by q sub v the size of the residue field, the ring of integers quotiented out by the prime ideal corresponding to v, then there is a natural surjection from the decomposition group onto the absolute Galois group of the finite field with QV elements. And the kernel of this map is what we call the inertia group, and I'll denote by I sub v. And as we all know, this absolute Galois group is procyclic, and one can choose a topological generator. And at this point, I guess I need to make some choice. So I'll declare this to be the geometric Frobenius. So the one that sends an element in the algebraic closure of FQV to 1 over Q, to the QVth root. Now, I'll briefly recall the Chebotarev density theorem, since it will be useful in the following. So for any Galois extension f prime over f, finite or infinite, that is unramified outside a finite set of places. I'm afraid outside finite set S of places. So this means the inertia groups for places outside S have trivial image in the Galois group of F prime over F. So if we have such a Galois extension, then if we look at the union of all the conjugacy classes of these Frobeniae outside S, so these angular brackets I used to denote the conjugacy class in G sub F. This union is dense in the Galois group of F prime over F. And now one of the main goals of number theory is to understand this absolute Galois group G sub F with this additional structure. So and one way to learn something about this is by studying representations. And since we have this topology, we study continuous representations. So representations of GF with values in GLNR for certain topological rings. So e.g. the complex numbers or algebraic closure of the L-adic numbers or algebraic closure of the field, the finite field with L elements. In subsequent talks today, there will be other choices as well. So this is the big, the holy grail. If we understood all these for all n's, we'd know quite a lot about the absolute Galois group of Q and of all its finite extensions. So some examples of such representations. Firstly, if R is equal to the complex numbers, we call them Artin representations, and they all arise because of the different topologies on the absolute Galois group and the complex numbers. They all arise from finite Galois extensions. So the projection of G of F onto this finite Galois group and then any n-dimensional complex representation. If we were to fix an isomorphism, just a ring isomorphism of QL bar with the complex numbers, this would be a special case of an L-adic representation. This does not, so Artin representation can be viewed as special cases of QL bar representations, but not vice versa, because we can have infinite image, and the standard example here is the cyclotomic character, which I'll denote by chi sub L. So this is a representation taking values in the L-adic integers, or the units. So just to reinforce this would be a one-dimensional L-adic representation. And this is defined by its action on, so if zeta is an L power root of unity, then chi L of sigma is the L-adic integer that defines me to what power I get mapped. Okay, so a third example, and important for the talks today, will be elliptic curves. So, say, given by a Weierstrass equation over our number field F, as standard, we denote by E angular brackets n the n torsion points of the group of points of E over an algebraic closure of F. So n torsion points in E of F bar. And we know that this is isomorphic to Z mod nz squared and does have a continuous representation of the absolute Galois group on it. And if we just consider now so this is for any integer n. If I now look at powers of a fixed prime L, I can take the inverse limit over all these as n increases and obtain the L-adic Tate module. And similarly here, we now know that we have a rank 2 ZL module. And the Galois action on the L-adic Tate module defines as a two-dimensional Galois representation that I will denote by rho E sub L. So this is a particular case. In general, if one has a smooth projective variety, one can study its étale cohomology, and this is almost the only way we know how to find L-adic Galois representations. I'll make now some assumptions that I believe will hold throughout the day today so we'll now focus mostly on L-adic representations, so representations where this topological ring is QL bar. And the assumption I want to make is that all L-adic representations are continuous, and that they are unramified at almost all places. So unramified means that the inertia at V acts trivially. And we want this to happen for almost all places. So all but finitely many. And the third assumption I'm not going to make explicit, but we want the restriction of our representation to decomposition groups at places dividing L to have a certain property that is called the RAM. So I don't have time, unfortunately, to make this more explicit, what I can say is that, so I'll combine these three assumptions under the named geometric. All representations arising from the Italic homology of smooth projective curves do have these properties. Now, very useful result is the following. If we have a semi-simple L-adic representation, then this is determined by the values of rho on Frobeniae where this notion makes sense, so where the representation is unramified. If you look back here, it does make sense to talk about the value of rho on Frobenius. We just take any lift of our choice here. So it's determined by the traces on the Frobeniae are for all V where rho is unramified. And there's a similar statement for mod L representations. So if I have a representation taking values in GL and FL bar that is semi-simple, then this is determined by, I might have to also consider the alternating powers of, sorry, let's trace here, alternating powers from 1 to n, but have a similar characterization. So the first result is combination of some general characteristic zero result about representations plus the Chebotarev density theorem. The second result, I think, is credited to Brouwer and Nesbitt for mod L representations. Okay, so this proposition allows us to make the following definition. Given an L-adic representation, because of the compactness of the absolute Galois group, one can find an integral lattice. This is not unique in any way, but we can choose such a lattice. So we then have that our representation is similar to a representation taking values in GL and ZL bar. So this is by yes. So the compactness and the category here. And by part B, I guess, of this proposition, what is well defined is if I now take the projection, so I've fixed some embedding and I've got a unique prime above L here, and I'll take projection down to FL bar, so rho prime mod L. This is, if I take the semi-simplification, this is well defined now, and I'll denote it by rho bar. So So given an L-adic representation by rho bar will denote this mod L representation here. And now to conclude the section on Galois representations, I want to make one more definition, and that is about associated L functions. So for this, I will now go ahead and fix a ring isomorphism between QL bar and C. This is slightly ugly, but simplifies now my exposition. So the definition is, don't know if there's a unifying name for the functions, but it's going back to Artin, Hasse, Wey. Define the L function here as an Euler product over all places where each Euler factor, in fact, depends only on the restriction of rho to the decomposition group at V. And I'll give you the recipe for all finite places not dividing our prime L. And this is given as characteristic polynomial of Frobenius on the covariance with respect to inertia. So determinant of 1 minus, I'll write rho sub IV for the covariance. So a characteristic polynomial, the reciprocal of that. For V dividing L, this requires some periodic Hodge theory. So thank you. The L-adic Hodge theory. And also at infinity, I won't give you the recipe there. But and as I've written it now, in this generality, this might not converge. We need to know something else about rho, like purity, to get conversion in some half plane. But just briefly, I guess, if I take the trivial representation, I recover the Dedekind zeta function. And if I take the L-adic Tate module, the dual of it, given my choice of geometric Frobenius, I recover the L function associated to an elliptic curve. So this is the L function whose factors at good places is equal to 1 minus AV of E, where this is related to the number of points over the residue field at V. At almost all. Okay, so this concludes the section on Galois representations, and I now move on to modular forms. And we'll mainly be talking today about Hilbert modular forms or generalizations. So I'll now restrict to a totally real field of degree m over q. And I'll denote by x the double half plane given by P1C minus P1R. So an upper half plane and a lower half plane. And I'll fix an identification of, so all embeddings of f into complex numbers take image inside R, and I take an identification of these M embeddings with the set from 1 to M. And I'll denote the images under one of these embeddings by x going to xi, so I in 1 to M. Okay, so we probably are all familiar with the action of SL2R on the complex upper half plane. And if one takes this double half plane, one can get an action of GL2R. And if I now take M copies, I can get an action of M copies of GL2R. And I'll fix an embedding of GL2 of my totally real field into these M copies using the M different embeddings. And a classical Hilbert modular form, excuse me, is now certain functions, holomorphic functions on M copies of the upper half plane, satisfying functional equations of the form. So for gamma, inside some congruent subgroup in SL2OF, so the ring of integers of the total real field, the value of f at gamma of t should be related to the value of f at the original point, tau, and it's related via this automorphy factor ci tau I plus di, whereby tau I also denote the components of tau in h to the m. So one has this plus other conditions. So this is not how I want to define my modular forms. Essentially, once the class number of the totally real field is bigger than 1, we should look at vector valued functions, and the definition of Hecke operators is also more complicated if we don't have principality of all our prime ideals. So the way to fix all this is to move over to the Adels, and I'll subsequently just write A and drop the subscript F, but I will always mean the Adels of my totally real field, not the Adels of Q. So briefly recalling definition of these Adels. So there's the Archimedean place and the finite Adels, and the Archimedean places is just F tensor over Q with the reals, and the finite Adels is F tensor over C with the profinite completion of the integers. And I'll now define some adelic Hilbert modular forms. So for U, a compact open subgroup of GL2 of the Adels, a function from M copies of the double half plane and a function of GL2AF taking values in C will be called a cusp form of weight K and level U. So for the purpose of today, it's enough to stick with a parallel weight k. So I will do that. So there's just one integer here. One could take an m tuple of integers. So what should this function satisfy? Sorry, I'll also subsequently shorten this to saying f lies in sk of u for cusp form of weight k and level u. And the properties this function has to satisfy is that it should be holomorphic in the first variable. Secondly, that it should be right invariant under the compact open subgroup U that I've given myself here. So I can have GL2AF acting on my functions by right multiplication on the second argument. So this should be invariant for all U in my compact open. And the corresponding automorphy property to the classical forms here takes following form. So for gamma in GL2F, this can act now both on the first and the second variable. This should be related to the value of f at tau and h. By the following factor. So the determinant of gamma to the 1 minus kth power, and then ci tau I plus di all to the k. There's two more properties. So if f is q, we also demand that this function is holomorphic at the cusps. The Kesher principle for total Lie fields different from q, this is automatic. And lastly, the cusp form part. So far I've defined modular forms, and now cusp forms. I also want that it vanishes at cusps. And these last two, I'll not define explicitly. Okay, so in the interest of time, I'll also not now give any example of any modular form. The examples I could give would be, I guess, once you are hopefully familiar with for f equals q, like the delta function, or I write down an Eisenstein series. I'll make clearer later on why we actually care about modular forms today. So I'll take now the direct limit or union over these spaces for varying u, and denote that by sk. And as mentioned before, we have an action of GL2AF on there by right multiplication on the second argument. And it's a fact that this representation is admissible in some technical sense, and decomposes as a direct sum of irreducible subrepresentations, which I'll call cuspital automorphic representation of weight k. So they're just representations of GL2 of the finite adults. Direct sum. And okay, just briefly, because it might help for later talks, I'll mention that the theory of automorph representations tells me that this will be a restricted tensor product over local representations. So one can, yeah. Important part is then the study of local representations of these GL2 completions at various places. I'll now define one particular compact open subgroup. I'll denote it by U1 of n, so where n can be any ideal in OF. I'll just stick with normal script n. And it will be invertible matrices with entries and the profinite completion of the ring of integers of the Hilbert at the totally real field. And they should be congruent modulo n OF hat to matrices of the form 1 star 0 star. And I'll write sk of n for sk u1 of n. So to relate this back into classical theory, if F is Q, if I take the intersection of this compact open subgroup with GL2 of Q, I recover the congruent subgroup gamma 1 of n. Or maybe with SL2Q. Now, I need to define Hecke action, and this can be written as the action of double cosets on these modular forms, and it sends a function to the sum of the translates under the right cosets of my double coset. And for U equal to this particular congruent subgroup, I make the definition of an operator called TV. So for pi v, a uniformizer of Fv, it's the action of the double coset given as follows. So I tell you the entry on the vth place, and it's the identity at all other places. And for v not dividing the prime ideal n, I define some other operators given by the double coset pi v on the diagonal. And now tk of n is so-called Hecke algebra, and I define it as the complex algebra generated by these operators I just defined, acting on the spaces sk of n. And one can show that this is a finite commutative C algebra. So since this algebra is commutative, we can find common eigenvectors. So let f be such common eigenvector of Tkn, which I'll shorten in the following to Hecke eigenform. And associated to an eigenform, I define a algebra homomorphism from the Hecke algebra to C that maps each Hecke operator through the eigenvalue. And I'll define coefficient field of f to be the image of this homomorphism, and the finite dimensionality up there tells me that I get a finite extension of Q here. Okay, so now the corresponding definition to what's still.
Kn is a C algebra, so unintentionally your Kn is always C.
Ah, yes. Thank you.
So you replace C with Q, it's now finite.
Yes, let's take. Thank you. Yes. So, yeah, up here we still have the definition of the L function for a Galois representation. I now define an L function for each such eigenform. So for places not dividing a prime ideal, the Euler factors are given by 1 minus lambda f of tv qv to the minus s plus lambda f rv qv to the 1 minus 2s. And for places dividing n, as they're given like this. And this is in some restricted sense today why we care about the modular forms, because we know that these L functions, well, they firstly converge for a sufficiently large real part of S. But since so I've given the definition using eigenvalues, one can also achieve this as a certain Mellin transform of the cusp form. And this plus the functional equations of the Hilbert modular form allow one to show that one has a holomorphic continuation and a functional equation the nicest form of functional equation would require me to have defined what a new form is, but I guess at this point I could say for each pi there will be a particular choice of f that then here gives me a functional equation relating f to a contragradient. Okay, so it's also us to talk about a special case that will be useful for the proofs later on. So one can generalize, of course, these Hilbert modular forms in lots of directions. One way to view them is that we just did something for this matrix algebra, 2x2 matrices with entries in F. This is a particular quaternion algebra, as in the central simple algebra of dimension 4 over our total real field. And we can do a similar, or can similarly define modular forms for other quaternion algebras. And one that we will make use of is for the special case where the totally real field has even degree over Q. we let D be the unique quaternion algebra that is ramified at all infinite places. So that means that tensored with Fv, it's isomorphic to the quaternion algebra, and unramified at all finite places, which means that at the finite places it does look like the previous quaternion algebra. And the fact that our field has even degree means that such a quaternion algebra exists. By choosing a maximal order, I can fix an isomorphism of D tensored with the finite ideals with GL2 of AF, a topological isomorphism. And for similar, as before, for compact open subgroups U, I can now make the definition of modular forms of level U. But I will just restrict to weight 2 now. So denote this by S2 superscript D of U. They're now functions on the double coset D tensor AF cross, quotient out by D cross, and quotient out by U. I'm not finished with the definition, but I just want to remark this is now a finite set. So this is why these modular forms are a lot easier than the previous definition. We need to quotient out by certain trivial functions. So functions that factor through the reduced norm. Again, apologies for not having time to define it, but for something related to the determinant. As before, we have an Hecke action of double cosets, and the miraculous result is that these seemingly simpler modular forms, so this is a result of Jacques Langlands and Shimizu, that these weight 2 forms defined for this definite quaternion algebra are isomorphic to the weight 2 forms previously defined, and in fact compatible with the Hecke action. Okay, so this concludes the second part, which leaves me now maybe 10 minutes to talk about modularity. So how are these topics related? They're related by a very big theorem due to many, many people. I will not be able to credit everybody. I'll just write a few names. So Eichler Shimura for Q and weight equals 2, Deline for general weights, and then Carayol, Wiles, Taylor, apologies if there's anybody in the audience who, yeah, I should also credit. Yes.
You did the partial weight one.
Yes. Okay, so what does this theorem tell me? That it tells me that if I have a Hecke eigenform, that I can associate to it a Galois representation. And I can associate one for every prime of my coefficient field. Let's denote the underlying rational prime by L. So I can associate to the Hecke eigenform an L-adic representation, and I'll denote it by rho f lambda. So two-dimensional L-adic representation taking values, in fact, in this finite extension. And its properties are that it is absolutely irreducible. It is unramified for places not dividing L or the prime ideal N. And the local L factors that are defined in both cases match up in fact for all the not dividing L. So this last statement in particular means for places not dividing L or N that the trace on Frobenius matches the Hecke eigenvalue of the TV operator.
You need to make sure that your isomorphism kf lambda bar to C induces on kf canonical inclusion from kf.
Yes.
If kf isn't just a number field, it's an explicit subfield
Yes.
of C.
Can I leave it as a comment? Yes, you're right. One last property. Well, I won't write it, is that these are also odd in the sense that the determinant of this representation on some complex conjugation is always -1. So what do we now mean for an L-adic representation to be modular? Well, this is if there is such an eigenform and prime such that rho is isomorphic to these representations here. So, and prime lambda dividing L such that rho is isomorphic to rho f lambda. And a similar definition for mod L representation that are irreducible. So why do I define modularity both for L-adic and mod L representation? Well, because a very important technique, and one that will be the topic of the second talk after lunch, are modularity lifting theorems. If one, for some reason, knows that the mod L, the residual representation of an L-adic representation is modular, then under suitable conditions, one can deduce that rho is modular. And now, the beginning of all these modularity results is the proof of the Taniyama-Shimura-Wei conjecture by Wiles, Taylor-Wiles, Broyle, Conrad, Diamond, and Taylor. That says that if I take an elliptic curve over Q, then rho EL is modular for some L, which in fact, so they prove this, and one can show that this is equivalent to having modularity for all primes L, and is equivalent to the existing and eigenform f of weight 2 and some level, such that the L functions of the eigenform and the elliptic curve match. And this is how one deduces that the L function of the elliptic curve has holomorphic continuation and functional equation. So might be an interesting exercise for those who haven't seen it before, to using the proposition I stated in the first part of the talk to prove the equivalence of these three statements.
Rho EL star, the way you said it?
Yes.
On the other side. There.
Thanks.
That's the correct thing, right? That's the Italca one.
Yes. Okay, my choice of geometric Venus at the star results now here in this star. Okay, so this has been generalized to certain totally real fields, but what we will talk about today in the 4 talks is, well, I guess the most general result in this direction, which is that if A is a elliptic curve over a totally real field F, that there then exists a bigger totally real field F, such that rho E L star restricted to the Galois group of this bigger field is modular. And this goes under the name of potentially modular, hence the title of the workshop today. Okay, so, and maybe,
So, you actually, but modular, you don't know it's an elliptic curve. It should be somehow even. I mean, there isn't an elliptic curve over 5.
Yeah.
It means literally that it's isomorphic to an elliptic curve.
Well, E is an elliptic curve, right? You've given an elliptic curve. We're not given a rho, we're given an E in this thing.
Right, and so you get a.
So you just consider E over F prime. And now it's
And now it's modular.
Yeah, absolutely.
yes. Sorry, I just stated it
Geometric sense,
in
not
this
the
way.
sense that there's not in the geometric sense, not in the sense that one knows that there's a Shimura curve or something for
Right.
parametrizes the.
Yeah.
There is an orthomorphic representation.
Yeah, the modular parametrization does not generalize to all totally real fields. There are certain cases where one still has something similar. Okay, maybe if I can, I'll just finish with a statement of some conjecture, combination of, I guess, Fontaine-Mesa and Langlands, that there should be a correspondence between, so not just for elliptic curves, but for general irreducible geometric analytic representations. They should be in correspondence and via their L functions to certain cuspidal automorphic representations. Of GL2 of AF. And there should be functoriality in, well, one can vary the group here, change to GLN, other groups, and functoriality also so operations on this side, restriction to a subfield GF prime, the Galois representation of an extension, there should be a corresponding operation on the other side. This is the base change operation. So, since I'm at the end of my hour, I will stop here. But after lunch, yeah, Fred will talk about these modularity lifting theorems. Thank you.
Are there any questions?
One comment is that the conjecture is that f prime equals x.
Yes,
All elliptic pairs are conjectures.
but yeah, in this generality, or for general total real field, this is the strongest result we know at the moment. But yeah, the conjecture would be that this is possible over f itself. Yes? So, several names. Taylor is main person. I'll leave it to the other three speakers to mention all the names that come into the proof of this theorem. Yes.
Just a comment about terminology. I saw your definition of geometric included the quotation mark. You wrote geometric with quotation mark.
Yes.
I mean,
Well, yeah, that is a, yeah.
since there are so many experts, I thought I'd make a terminological suggestion, or humble one. That, this geometric should be called weakly geometric. Very confusing the way it's usually phrased. Weakly geometric, I suggest. That's right.
So I believe Taylor maybe calls it algebraic to match the algebraic on the other side, and reserves geometric.
Taylor's been saying.
But
So the idea is got to be rho. What does it mean for rho to be unramified outside of finite state?
Yeah.
What does it mean for rho to look like it comes from geometry? That's like everybody calling it geometric.
Yes.
I mean, that wasn't.
Yeah, algebraic. Richard says geometric should mean does come from geometry, and algebraic should mean should come from geometry. That's my understanding of what Richard's.
Weakly
But
geometric.
surely
can
algebraic
be-
is something about what happens in infinity.
Yes, for cusp forms,
Yeah.
that's what it means. But cusp forms automatically have this unramified outside of finite set of places. It's tough. You've got to be careful. Geometric. You don't want geometric to. Geometric looks like it means it comes from geometry, and that's the conjecture.
Yes.
So the terminology is maybe wrong, but maybe Minhyung's idea.
With the quotation marks, it's clearer. Yes.
Yeah, but then it's hard to say.
Okay, so we can continue the discussion over lunch. Now, I just remind everyone that I'm afraid to get lunch, you have to have registered beforehand for the catering. So everyone who's registered, and of course this distance, the formal classes on program. So let's thank Tobias for